Welcome back. This is the second part to a couple of videos just relating to an Access to Science course on electromagnetism, and we're going to look at eddy currents and eddy current losses, whatever the heck they are. All right, so the idea is, maybe first of all, what do we mean by an eddy? So if we have a river, okay, and normally a river would water would flow down a river where there's banks either side, but if there's maybe sort of a difference in the shape, or there's some rocks in there in the river, then what we find is as the water sort of flows past it, then we get these sort of swirls that are produced, and these little swirls are called eddies. So this circular motion of the water is called an eddy. So we're going to look at eddy currents to do with electricity flowing. And so what we know already is that when we have a magnet or a wire in the presence of a magnetic field, is that as we move that wire in that magnetic field, it causes electricity to flow along the wire. All right, now that's all very well when you have a thin, narrow wire, but what happens if you have a magnetic field, and rather than having a small wire, thin wire, we actually have a disc. So how would I draw that? Something like that, a disc. And so as long as that thing's moving, that could be spinning, we're going to induce a voltage or a current in that disc. Okay, and because it's not a thin wire, what we find is that we get sort of eddy currents. The electricity does flow, but it flows in the circular sort of path. These little eddies are created as the section of the disc passes through that magnetic field. So these are the eddy currents that we're talking about. Okay, and the reason we sort of have that is to do with the fact that when we have a force on the wire in the presence of a magnetic field, we've got these charged particles, and it creates a force on these charged particles, and this is always at right angles to the motion. Okay, and so because if that's the motion v for velocity, then we have this force in this direction at right angles, and this and as the electrons are moving in that direction, they've got a force in that direction. Well, the force will cause the electron to sort of go down here, but even though now that it's changing in direction slightly, well, the force is also still at 90 degrees, and so we get this sort of circular path created, and that's what these eddy currents are. So that's an eddy current. We talk about eddy current losses, so let's just have a quick think about them. Which is predominantly what we're looking at in our specification. So what's an eddy current loss? Let's write that on. So an eddy current loss. So essentially where this becomes important is for transformers. Let's get back into focus. So with transformers, we're using Faraday's law of electromagnetic induction, and essentially we have one coil on one side, we have another coil on the other side, and then we link this, very sort of simplified diagram, we link this with an iron core. So this is our primary coil, this is our secondary coil, and so by having an alternating voltage on this side, this creates an alternating magnetic field, and this changing magnetic field, Faraday's law, induces an alternating current in this coil. Okay, and we're linking it with simply a bit of metal, and this focuses or concentrates those magnetic field lines. Okay, now this is a large area, and again, this changing magnetic field it causes electricity to be induced not only in this coil, but also in this soft iron core, we call it. All right, and because this isn't a narrow wire, well, we're going to get eddy currents generated or created in this thing. And of course, what's happening is we're getting electrical energy. We really ideally want 100% of that electrical energy to be transferred to this through electromagnetic induction. Okay, but if we're causing eddy currents in the soft iron core that links those two coils, then this is electrical energy, and we're losing some of this electrical energy by creating these eddy currents. Okay, and that's an eddy current loss in this system. So we want to eliminate or minimize those eddy currents. And the way we do it is when we look at that lump of metal, is we don't have a big block like that. We split it into layers. And so we have a little bit of metal, and then we have basically a resin, a glue that glues all these layers together. By laminating, that's the process. By laminating the core, it means that these eddy currents, they're not able to flow between these layers because we've got an insulator, an electrical insulator between those layers. All right, so we don't get the big ones, but we might get ever so slight small ones because of the thickness of those layers in this soft iron core. But the metal is able to focus and concentrate that magnetic field so that this secondary coil experiences as much of it as possible. All right, which makes it as efficient as possible. And I'm sort of roughly told, I read in places that it's about 98% efficient, which isn't bad, frankly. In the whole process of taking electricity from a power station to somebody's home, we get more losses in other areas of this. The fact that in the transformers in that process that are used has, a 2% loss. That's quite small relative to the rest of the losses involved. So eddy currents are the way that we cause these electrons through a change in magnetic field to sort of move in a circular path. That's electricity. We're creating an electric current in here. One thing I didn't say is that, and this electricity moving through this metal wire, or rather the soft iron core, this will have an electrical resistance, and so in actual fact it would end up heating up. So we get energy losses as heat to the surroundings. By laminating it, we have very much smaller eddy currents created because it can't flow any further, and as a result of that, it reduces the heating effect. Hope that made some sort of sense. Thanks.